Hello, everyone, and welcome back. My name is Kevin, and today we're going to be going through another data structure, which is a prefix tree, or more commonly known as a trie. So a trie is going to be used to store some set of strings, and it can be used in autocomplete, spell checking, and a lot of other practical use cases. So let's get started. So the first thing we have to think about is why is it called a trie? So if you ever think about the word retrieval, you pronounce it as retrieval, like a tree. And we don't really want to reuse the name tree. We already have a bunch of trees. We have our binary trees, our prefix trees. So we're just going to kind of pronounce it as a trie, like a try, and that's just where the name comes from. Okay, so with that out of the way, tries are going to be a tree used for storing strings. Let's quickly define a string real quick as some sequence of tokens, where the tokens are all going to belong to some alphabet. So just for the purpose of the video, the alphabet I'm going to be using is lowercase English alphabet A to Z. And then, a string is going to be some combination of characters from this alphabet. Okay, so with that out of the way, let's say I had some set of strings and I wanted to see if a given string was in that set. So some common approaches that I might do is, let's say I just had some arbitrary set that I'm just making up right now. And let's do that. Okay, so if I wanted to check if the string ln was in this list, what would I do? I would start at the first element, compare C to L, not the same. Move on. A to L, E to L, L to L, okay. M to N, not the same. And finally, the last element, L to L and N to N. So what I just did there was I had to parse through individually through this list and compare each character at a time, because that's how string comparisons work. So the time complexity of this is going to be O of N, where N is the number of strings in my list, times where M is the maximum length of any one of these strings. Not terrible, can we do better? Well, let's just assume for a second that we have the ability to sort the list. We could definitely get better with that. If I had AG, CD, EM, LM, and LN. If we have some sorted lists, then we can do a very similar operation where we just end up converging in log n instead of n, and still times that n. Okay, any better approaches? Then the next best approach that we can have is probably something with a hash. So say I just made, some hash table. There's some arbitrary hashing function that we have. And let's say it kind of, gets something like this. And then if I still want to look for ln, I can directly hash to it. And this is now going to give us some comparison in O of m time, where, we just have to still compare our m letters, but that's all we really have to do. So hashing is clearly the best option, but it's very limiting. We can only look for our exact key. Let's say I wanted to find something that was like ln. Well, that could be in a completely different spot. Maybe that's, up here with en. There could be no connection between ln and lnn. So can we resolve this problem with some tree structure? So let's just say we have a tree with some arbitrary root that isn't really defined as anything. There's no value stored in, it's just our starting point, so we can build a tree off of this. And then from this root, we have, in this case, 26 things that branch off. So 26 is clearly going to represent all letters of the alphabet. I'm not going to write it all because that's a lot. But let's say we have a C right here, a D right here, and a R right here. So just with that, you can already kind of see where this is going. We can very quickly division our words into some form of tree. So C can kind of go into a cat, right? But it can also unrelatedly go into clown. Well, D can just maybe have a dog right here. And let's have R go rat, maybe. And let's do rats plural. Then all we have to do in this tree structure, mark each of these words as an ending point. So cat's an ending point, clown's an ending point, this G and dog's ending point. We have this T and rat and this S down here because they both form words. So now we've stored the words cat, clown, dog, rat, and rat. So that's 5 words in this tree structure. And if I wanted to search if, say, the word dog was in here, well, that's going to be a O of M operation for a search. All I have to do is start at the root and go through up to M letters, where M is going to be the maximum length of my word, and check for that. So I just have to check for D, then O, then G, and is G marked as an endpoint? It is, so we're good. If I wanted to find something like dogs, well, I would get to the G, and there would be no S below it. Even if I had an S below it, if it was not marked as an endpoint, then the word dogs would not be considered in my list. Okay, pretty simple. Let's do another algorithm. Let's do insert. Well, insert is also going to be pretty much just as easy. We start iterating down our list. Let's say I want to insert dogs. Well, I would just go, is there a D already? There is. Perfect. Is there an O already? There is. Is there a G? There is. Is there an S? There is. Is the S marked as an end? It is not, so we mark it. We just inserted the word dogs. Let's say I wanted to insert the word raft, R-A-F-T. Well, is R here? It is. Is A here? It is. F is not, so we're going to insert an F going off of A. And then there's definitely not going to be a T below it, so we'll insert a T below it and mark it as an endpoint. And just like that, we inserted it. And they can probably guess there's going to be a lot of pointers involved. Every one of these nodes is going to need up to 26 pointers in this case. It's going to need a data entry. It's going to need a Boolean if it's completed or not. And we'll talk about some ways to compress those later. But for now, yeah, it's a lot of space, but we can get some search very, very quickly. We can get an insert in just as much time with O of M. So it's definitely going quite well. Let's talk about delete. Well, the easiest way to do delete is to just remove this little check mark that I talked about. Let's say I want to delete the word rat, but not rats. Well, all I have to do is go here, go to R, go to A, and go to T. Check mark, great, let's delete that check mark. And we're done. That's all there is to it. And with that in mind, we can see that delete is probably going to also be O of M, as we're going to still have to iterate down that list. Now, just in terms of data management, let's say if like this S down here was also deleted, then you could go back and clean up. And it's pretty intuitive to see how you just need to iterate through the list. And if something is involved somewhere else, then we leave it, but if not, we delete it. So in this case, the S could very easily be deleted, has no children. That T now has no children, so we can delete it. A has a child, so we leave it alone. Either way is fine. Just whatever you need for your specific case. Okay, so with that in mind, let's talk about autocomplete. So let's kind of use this try that I already have prepared down here. So, same thing where we have some sequence of words right here, and we have it kind of drawn out over here. And another thing to keep in mind is say the word car is technically visible in this try, but I don't have it marked as an endpoint. So we're not considering car as a valid word, but cart is going to be a valid word because we have this T marked as an endpoint. So, let's say I'm just, at Google and I type in CA. Google is now going to give me a list of possible responses that could fill in that CA. And obviously, there's going to be a much bigger data set than just this try right here. But what are some ways that we can kind of solve this problem? So we're going to have, our first step is to iterate O of P, sorry, O of P down our try, where P is going to be the length of the prefix. Nothing crazy. If there's two characters in my prefix, I iterate two down. Not a big deal. And then now we have a couple of options that we can do. The first is going to be a breadth first search. So I'm not going to go in the full logic of a breadth first search, but I'm going to run one on this tree. And let's just say for the sake of Google, obviously we can't have unlimited things, that we're only trying to find three possible, recommendations for the autofill. So if we were to implement a BFS on this, well, we would kind of need a queue going off of this A, you know, looking at all of our possible letters. So our queue is going to start off by having a B, a C, and an R. Okay, so now that we branch off of A, let's check these things. Is cab CAB a valid suggestion. It is, because this B is marked as green. So we're going to mark cab as, a special word, and then we're going to pop B from our queue, and we're going to add B's child, which in this case is going to be BI, because B only has one child. Okay, let's keep going. CAC isn't valid, so we're going to pop C and put CT at the end, because C only has one child. CAR isn't valid, so we're going to pop that R and put an RT at the end of our queue. Let's keep checking. CABI is invalid, so we're going to pop that. And now bin is going to go at the end of our queue. CACT is invalid, so we're going to pop that. And now we have two things that are going to show up, cacti and cact2. So it's going to be CTI and CTU. And now we end up at cart, CART. That is going to be a valid word because that T is marked with an endpoint. So we have cart over here, and cart does have children, so we can pop that RT and then add, sorry, wrong color, add that RTO over here. CABIN, even though cabin is a real word, is not marked as a word in our tree, so we're going to pop that and put that BINE at the end of our list. Now we end up at cacti. That is a valid word, and that is going to be the end of that section on the tree. So if we were to pop it, there would be nothing to add. And just like that, we have our three words that we're looking for. So, the BF, it's going to be kind of incrementing universally as we go down this tree altogether. And the next word that would show up would end up being cactus, and then cabinet, and then cartoon. But we limited to only looking for three words at a time. So we'll get the three shortest words that can fill in the CA phrase. Okay, not bad. We have another option though. And the other option is going to be a DFS. So this DFS is going to use a stack. And the purpose of a DFS here is going to get some kind of priority for certain things. So let's just try it with alphabetical order. So we're going to push onto our stack in reverse alphabetical order. That's going to give us R, C, and then B, with B being at the front of our stack. Okay, so we can find, CAB, once again, going to be the first word we find. Then we're going to end up popping B, but adding B's child to the front of our stack, so we add BI. We'll pop BI, add BIN, pop bin, add BINE, pop that, add BINET. Okay, so the next element we're going to go for is going to be cabinet. Then we can pop that, there's no children, nothing to add. So now the front of our stack is going to move over here to this CAC. CAC has nothing, pop that, add a CT, nothing. Now we're going to pop that and we're going to add CTI and CTU. And we're going to get cacti. And then we would pop that and our stack would move over to the CTU. And by doing it this way, hopefully you're noticing that we're actually getting our words in perfect alphabetical order. And if we were to continue this, we'd get cactus, cart, and then cartoon. So with all this in mind, this actual searching part of our autocomplete algorithm is going to take some kind of O of k times m, where k is going to be, the number of things that we want to find. So if we only want to find three things, then it would be that. If we want to find, an arbitrary big number of things, it would approach that number, times m, where m is the possible longest sequence that each of these words can be. The DFS can also be used in other applications. Say that I have some kind of priority for these, where maybe the word cacti has a very high priority, while cartoon has a very low priority, because not a lot of people search for the word cartoon. Then I can kind of rank these options on this try so that certain things have higher priorities. And I put those, closer to the top of my stack, so I traverse those ways more often. That is going to require some additional data, but it is something that Google is going to use, where certain things show up a lot more often when searched So we want to use those when we're auto-completing. Okay, with that all in mind, there's only one more thing that I really wanted to go over, and that is just kind of an introduction and how we can compress these tries. So if we look at this, there's a lot of information being wasted here. I, as a node, needs to hold a Boolean, okay, but it also needs to hold a bunch of possible pointers that there's not really any need for. So what we can do is we can kind of merge this up. If at any point a node has only a single child, then we can merge that all together. We can very easily turn this entire section into a single node that just says cabinet. Or sorry, without the CA though. And that can be marked as an ending node. And no information is lost by doing that. So this middle section, that C and T can be combined together. We can now have a child that leads to this I, or a child that leads to U and S put together. And all we're doing is compressing. Same thing right here, where we would need a RT to be together, and then OON child. And just like that, we can just compress our try and use, a lot less space. So, our delete still gonna have the same thing, or we can just remove that green box. Our search gonna be the same possible pattern. The only difference that's gonna affect anything of the algorithms we talked about previously is insert. Let's say I kind of came across the word cars. So I wanted to insert cars into this. Well, in that case, I would need to break this up to have kind of something that looks like this. Sorry. Um, the R would need to have a child that's a T, which would be marked as an ending point, and then the T would go to that OON, but then the R would also need to have a child, which is just an S, which would also be an ending point. So we could have to do some cleanup as we're inserting into a compressed tray, but there is, a lot more opportunity to save memory here, which is going to make our try a lot more efficient. Hey, that's all I had for today. Thanks for watching.